Good morning, everybody. This is lecture 1 on statistical computing and machine learning. This is an introduction course to machine learning from a probabilistic Bayesian perspective. So in the first few lectures, we will cover some of the basics of probability and statistics. Obviously, this is not an introductory course to probability and statistics. I'm assuming you already have some knowledge of these concepts. So I'm going to try to at least bring up the notation so we are all understand the subsequent lectures starting with the same background. So the lecture today will involve some of the definitions from probability theory, and we will introduce the Bayesian perspective. We will discuss about discrete random variables. We will introduce the Bayes rule. And I will complete the lecture today with the definition of independence and conditional independence of random events, and which we will see subsequently leads to the same concepts for random variables. So the goals for the lecture today are to understand the probability definitions and the notation used, to introduce and start using the sum and product rules of probability, and become familiar with using the Bayes formula, and at the end understand the concept of independence. A little bit about the various books where you can find material. The key undergraduate book here is the book by Bertsekas and the online resources at MIT. So this is a very good book at the undergraduate level. The machine perspective of probability, you can find it in the books by Chris Bishop on chapter 2, or Kevin Murphy's book on chapter 2 as well. And in some sense, I will be following this machine learning perspective in this course. All right. So we have two views of probability, and the frequentist and the Bayesian perspective. And the frequentist view is we're looking at events that repeat themselves, and we're asking what are the frequencies of these events, how often do they happen. The Bayesian perspective quantifies basically uncertainty about events that don't necessarily happen repeatedly. So you can actually look at events that may happen only once in a lifetime, and you're asking what is the probability that these events may happen. So obviously you cannot repeat these experiments to come up with a frequentist probability definition for this type of events. We're going to need this new way of thinking, which is the Bayesian paradigm. And if you ask where is these probabilities come if the events don't repeat themselves, well, you can think that quantifying these uncertainties requires models, for example, and these models may be wrong, or they may not be perfect. So the way we compute these uncertainties will induce uncertainties coming from wrong models, maybe uncertainties coming from the type of data that we use to do inference, and the like. So we will see lots of these ideas in this course. So, for example, you may ask yourselves and say, what is the probability that the polarized cap will melt by 2020 or 2022? So this is not something you can repeat constantly, so it requires some mathematical model, and that mathematical model obviously is going to be very complex with uncertainties, and these uncertainties will propagate to the calculation that you do for when the polarized cap is going to melt. And this is the type of events we're interested in a Bayesian setting. All right, the nice thing is that the rules of probability are identical if you use the frequentist or the Bayesian paradigm. So in the first few lectures, I'm going to be mixing the two, but again, keep in mind that our focus in this course is going to be on this Bayesian perspective of probability. All right, so let's introduce first this concept of sample space. So if you look at an experiment that has many outcomes, the sample space is the set of all possible outcomes of this experiment. So if you can think that you have a die with 6 different faces, let's say corresponding to the numbers 1, 2, 3, 4, 5, 6, this will consist from what we call the sample space that I denote here with a capital Greek letter omega. We're interested on events, and events are nothing else but a subset of the sample space. So when you look at this as a set, when you take subsets from omega, that's an event. So for example, in the die rolling example, the event E equal to 5 is the event of rolling a 5, okay? And similarly, if you look with playing cards, for example, this is the event that consists of J, Q, and K, which are the face cards. We are going to use often the notation for the union of events, and the letter used is standard from set theory. So this is the union operator. So you can talk about the union of 2 events, E and F, and basically the union is defined from all the outcomes that they're either in E or in F or in both E and F. Similarly, we can define the, okay, so this is an example of the union of this event E consisting of 1 and 5, and F consisting of 3. So the union of these 2 events is 1, 3, and 5. So we can define also the intersection operator, and the intersection of 2 events E and F that consists of all the outcomes that they are in both E and F. All right, so for example, if you take E to be 1, 3, and 5 and F to be 3, the intersection of E and F is 3, because 3 is an event within this E and within the F events. Now, in another example that we see here, the common event between E and F is K, all right? So that's the event of getting a king. Now, it's possible that if you take the intersection of 2 events, maybe the intersection is the empty set, there is nothing in common, and in that case, we say that E and F are mutually exclusive. So that would be something useful that you need to remember as we move along. So mutually exclusive, again, are 2 events that when you take the intersection, you get the empty set. Now you can generalize these definitions of the union and the intersection to infinite but countable events, and you can see here the union of the events E1, E2 to E infinity, and the intersection here of the events E1, E2, etc. Let me introduce now the rules of probability theory. And one of the fascinating things that we will find in this course, the rules of probability theory are very few, very basic, very common sense. Still, what comes out of it in the context at least of algebraic calculations can be very complex and able to address very important scientifically and technically speaking type of problems. So what are the rules of probability that we're going to be using? The following conditions need to satisfy. The probability of an event E has to be between 0 and 1. All right. The probability of omega has to be equal to 1, because you remember omega is all the sample space, right? And the probability of the empty set has to be equal to 0. If we have events that are mutually exclusive, then the following is to hold, that if you take the probability of the union of these events, this has to be the sum of the probabilities of each event. Now, there is much more to this last statement, and the fact that we have an infinite number of sets, but I'm going to leave the discussion out, and you can learn more in your basic probability books. For now, this rule again says that if you take the probability of the union of mutually exclusive events, this is equal to the sum of the probabilities of each of these events. And again, looking at all these rules, they are fundamental, and in many ways they are common sense rules. They are the same if you have the frequentist approach to probability or if you have the Bayesian approach to probability. So let me introduce the complement of an event E. So the complement is denoted E with superscript C, E complement, and it is the event that when you take the intersection with E, you get the empty set, okay, the empty event. So for example, if the event E is the event that when you roll a dice 3 times you get 3 sevens, then E complement is the the outcomes, all the possible outcomes that when you roll the dice 3 times, you get anything but 3 sevens. Okay, and let me just do sort of as an example a little bit of demonstration of utilizing these rules of probability that you saw in the previous slide. So here is an identity that, again, we will try to see what it means geometrically at least. It says if you have 2 events E and F, the probability of E and F is equal to the probability of the union plus the probability of the intersection of E and F. So think of this probability of events representing areas here in my geometric representation. So this square is my whole sample space, and this yellow circle is this area represents the events contained in E, and similarly these are the events in F. So this is again the yellow area is the probability of the event E. Similarly here is the probability of the event F, and on the right hand side you can see if you take the probability of the event E and F, this will be either being in F or in E or in both. When you take this intersection, you notice you're actually accounting for the common area between E and F twice, all right? Because you know, when I write this and you look at the probability of F and probability of E, this common area here has been accounted twice, so you have to remove it once, and if you do that, then you get this identity that is demonstrated there. I mean, obviously there are more mathematical ways to show this, but this is sort of a common sense geometric interpretation of this equality that involves the probability of the union and the intersection of 2 events. All right. Let me introduce discrete random variables. The discrete random variables can take values from a finite or a countably infinite set that I call here a calligraphic X, and we define the probability of the event capital X equal to little x as capital P of little x, and this is our definition of what we call the probability mass function, or in abbreviation PMF. All right, so again, capital X is a discrete random variable, can take these little values x, and we're interested in the probability of capital X taking this value little x, and we call that the probability mass function. Obviously, from the rules of probability, P of x has to be between 0 and 1, and then if we sum P of x for all possible values of x coming from this set calligraphic X, this has to be equal to 1. And I'm going to show you 2 examples of discrete random variables. One is going to be a uniform random variable that takes values 1, 2, 3, and 4. And another one will be sort of a singular, if you like, probability mass that can only take the value 1 when x equal to 1. So still, the values I consider are coming from this calligraphic X set, but the only value that is allowed with probability 1 is the value X equal to 1. So the last example, I'm going to indicate it with the equation that you see in the bottom. That is sort of a good place for me to introduce the definition of the indicator function. So the indicator function says that P of X is equal to this indicator function of X equal to 1, and this indicator function is equal to 1 only when X equal to 1, otherwise is equal to 0. So let me give you a graphical representation of the uniform distribution over this set 1, 2, 3, 4. So the probabilities of hitting X equal to 1 or X equal to 2 or X equal to 3 or X equal to 4 is 1/4. That's my uniform distribution. And here, this is my indicator function. It's a singular probability that can only take the value 1, and obviously it has to be with probability equal to 1. Okay, a very important now concept I'm going to introduce. Since we discussed about discrete random variables, I'm going to introduce the concept of the joint probability of two discrete random variables. So let me just put directly what the definition is. So we're going to look at two random variables X and Y, and we're going to ask what's the probability that capital X takes the value Xi and capital Y take the value Yj. So we're looking at both X and Y being discrete random variables, and I give you here a nice picture from Chris Bishop's book. So if you can think the random variable X taking only 5 values and Y taking only 3 values, you can ask what's the probability that X will be Xi and at the same time Y will be equal to Yj. So let's suppose that you're conducting an experiment where you randomly see the frequencies of how often X will be the value Xi and Y the value Yj, and let's say in n experiments n subscript ij, we do get X equal Xi and Y equal to Yj. So it will actually make a lot of sense then, using the frequentist point of view, to define the joint probability of X taking the value Xi and Y taking the value Yj as Nij divided by n. So I'm going to do a little bit of algebra now, and I'm going to do this algebra by first introducing in my capital N experiments, I am going to assume that X takes the value Xi Ci times. Remember, Nij is the number of times in n experiments that X takes Xi value, Y takes Yj, but now I'm looking at X alone, and I'm asking how often X takes the value Xi, and that number is Ci. So what I'm going to do is I'm going to take this joint probability and I'm going to write it as follows. So you remember my definition before, it was Nij divided by n. So now what I'm going to do is I'm going to write this Nij divided by Ci times Ci divided by n. All right. And now what is Nij divided by Ci? All right, using sort of a common sense, the frequentist concept of probability. Nij is the number of times that X took the value Xi, Y took the value Yj, and Ci is the number of times the variable X took the value Xi. So in this motivates, this Nij over Ci motivates the definition of a conditional probability, and I'm asking, out of the times that X took the value Xi, and remember those times are Ci in number, how many times the variables X and Y took the values Xi and Yj, and that is Nij. So I define this to be the conditional probability distribution of Y given capital of X. And then Ci over n is obviously the probability that X takes the value Xi, and that is what I call the marginal probability of X taking the value Xi. So that leads immediately to what I call the product rule of probability, which is one of the two very fundamental rules in probability theory that you need to understand, and you need to be able to use it upside down all the time. So again, it allows you to write the joint distribution of two discrete random variables to the conditional distribution times the marginal PMF of X. And later on, of course, we will extend this to continuous random variables. The equation will look identical, and instead of using probability of discrete events, we're going to use probability density functions, as we will see in one or two lectures from today. So that's the product rule, and notice because X and Y in the joint distribution are symmetric, right? So I can actually write, instead of having the condition of Y given X, I can write this, the probability of capital X given Y times P of Y. And we will use actually one or the other form depending on the type of application of interest. So that's the product rule for discrete variables. And on the top, I forgot to go through the simpler rule, which is the sum rule of probability, and effectively says that the probability of X taking the value Xi is the sum of the joint probability of X taking the value Xi and Y taking the value Yj for all possible values of Yj. Okay? So if you take the joint and you sum for all possible values of Yj, then you get the marginal distribution of P of X. Again, when we do later on continuous random variables, the summation here is going to become an integral, but you do understand that more or less they express the same thing that has to do with marginalization. We marginalize, we integrate Y out to get the probability of X. All right, as an example, when you read the slides, you can actually show that if you have d number of random variables and you look at the probability of x1, x2, etc., xd, you can actually write down this as the probability of x1 times the probability of x2 given x1, the probability of x3 given x1, x2, etc. And effectively, the way you will actually prove this equation is to start using the product rule one term at a time. So actually you can start from the end if you like, and you can write this joint distribution as the probability of xd condition on all the other random variables times the probability of all the other random variables, and then do again the product rule for the probability of x from 1 to d minus 1. And if you do this recursively, you will get this nice chain rule that is extremely essential in many calculations. Looks very simple. Of course, when d is very high dimensional, this equation also tells us how difficult or how computationally expensive it is to actually model the joint probability of many random variables. Okay, so here again is the summary of the sum and product rules of probability, and I'm writing, I mentioned the symmetric form of the product rule that you see on the bottom, and again the sum rule, rather than indicate the summation on indices, I sum on the y values, right? That's what it means. Take all possible y values and sum over them, and that's the sum rule of probability. Okay, now the Bayes rule, one of the most important equations in this course, to be used more or less in every lecture. So we have two, for now, discrete events, and we're looking at the conditional distribution of x given y. So if I use the product rule, I can write this as the joint divided by the marginal of y. Before, you remember, we had the joint as the product of the conditional times the marginal, so now the conditional is the joint divided by the marginal. And now what I'm going to do is I'm going to use in the numerator the product rule, but in a reverse order. So I'm going to take, here we have the condition of x given y. So here I'm going to write the condition of y given x times p of x. Okay? And now what is p of y, capital Y equal to little y? I indicate this with being this long summation, and you may wonder what exactly that is. And so if you look carefully at this equation, and I'm going to reveal the actual calculation, this equation comes from two steps. One, where you write this marginal p of y as the sum over all possible values of x of the joint p of x and y, and then you write the joint using the product rule that you see inside here. So let me show you the actual calculation. So effectively, I am writing p of capital Y equal to little y as the summation for all possible values of x prime. This is the sum rule of probability, and then inside here I have the product rule, and I'm conditioning y on x. And you notice, to avoid confusion with the notation, because I already have a little x here and a little y, I make this x prime, because this x prime is a dummy sort of integration variable, right? I'm using this variable in my marginalization process. All right, so let's do one example of Bayes' rule to see exactly what it means. And again, we're going to see this Bayes' rule in infinite lectures in different settings. So the earlier you understand how to use it and what it means and what the implications are, the better. So let's take an example from Bishop's book. We have two boxes, the red box and the blue box, and they contain oranges and apples. The red box contains more oranges than apples. The blue box contains more apples. Now what I'm going to do is I'm going to select one of those boxes with this, what I call prior probabilities. So the red box is going to be selected with probability 410, and the blue box is going to be selected with probability 6 over 10. So basically what it says, if I'm going to select this one of these boxes 10 times, right, 4 times I'm going to select the red, and 6 I am going to select randomly the blue box. So these are my prior probabilities. So here is the question that we need to answer. Suppose that somehow we randomly selected one of the two boxes, we put our hand in the box, and we remove one of the fruits from the box, and it comes to be an orange. And I'm asking you, well, what's the probability that the box where you select that orange is the red box? Right? So again, we select randomly one of the boxes, we select randomly one of the fruits from that box, it comes out to be orange, and we're asking what's the probability that the box where we did the selection was the red box. Now, before I do any calculation using the Bayes rule, you can actually sort of expect that this probability, this conditional probability, is going to be higher than the prior probability that was for selecting the red box, that was 4 over 10. And the reason is the fact that I know that I selected an orange, right? You look at the distribution of orange versus apples in the two boxes, and you know there are more oranges in the red box, so this probability is better turn out to be higher than the prior probability of 4 over 10. So how do you compute this probability? An application of the Bayes rule. So let me just put all the equations up, and you see on the Bayes rule here in action. So to compute the probability that the box was red if you selected orange, what you need to know is the probability that you selected an orange if the box was the red box times the prior probability of selecting the red box, and then on the bottom we had the marginal probability that the fruit you selected was an orange, And that marginal, you remember, by combining the sum and product rules of probability, can be written explicitly with this nice sum. We only have two options for the box, can be either red or can be the blue box. And these probabilities are all known. So for example, if I look here, it says if I selected the red box, what's the probability that I select an orange? So if I am in the red box, I have 6 oranges out of 8 fruits, so the probability is 6/8. The probability that I selected the red box, we can see here it's 4/10. And when you compute all of this sum, it comes to be 9/20. So this probability is 2/3, and not surprisingly, it is higher than 1/2, and so higher than the prior probability that this is that the box that I will select was the red box before I see any fruits. All right, so this is a very nice application of how the Bayes rule is used in action, and effectively it provides an answer to this inference problem. You know, if you say I selected an orange, it will tell you what is the probability that this orange came from the red box. Let me do another example, and again this is a nice sort of historical example in the context of medical diagnosis. So let's say that we're looking at diagnosing a disease, and in this case the slide indicates the disease to be the tuberculosis, indicated here as TB, and we're going to assume that 0.4% of the population have this disease. So this is my prior, this is what I call a prior or population prior, that any individual will have the disease based on statistics coming from the population, okay? And that probability, as you notice here, is quite small. All right, so let's say that there is a test that can diagnose if someone has the tuberculosis, but that test, like all medical tests, are not perfect, and we're going to assume that if you have the disease, the probability that the test will come to be positive is 0.8. So if, again, if you do have the disease, 80% of the time the diagnosis is that indeed you have the disease. All right, so if I ask you now, let's suppose that you take this test and the test comes to be positive. Obviously you will start worrying because you will get the impression that you have 80% chance that actually you have tuberculosis. But is that correct? And the answer is no, because you have not yet accounted for the fact that only a very small fraction of the population has the disease. So to account for this prior information in a Bayesian setting using the Bayes rule, we will see that the number that comes out is way smaller. So before I do this Bayes formula calculation, let me assume that if you don't have the disease, only, you know, the probability that you will be turned by the machine to be positive is very small. It's 0.1. Okay, so if you don't have the disease, the machine will tell you that you have it only with probability 0.1. So what do we need to calculate here? So let me pose the problem. This is what we need to compute. If the machine gives you a positive diagnosis, what is the probability that you actually have the disease? And that probability is not 0.8, okay? So how do we compute this probability of having the disease if the test comes positive? Well, is a direct application of the Bayes rule that you see in this slide. And I am not going to go through expanding every single term, but if I concentrate, for example, on the numerator, the probability that the machine will give you a positive outcome when you do have the disease, you remember it was 0.8, and the prior that someone in the population will have the disease, it was 0.004, and similarly we have all of these terms in the denominator. So when you compute all of these things, the probability that you have tuberculosis when the test comes positive, it's not 80%, it is 0.031, right? So in some sense, if you have a device that diagnoses a disease with probabilities of giving you a positive outcome when you have it to be only 0.8, you notice this leads to extremely small probability of literally having the disease, which means this test is not very accurate, and in some ways it's a waste of money to even take the test. All right, let me do another example, and in some sense a little bit ahead of our course, but I wanted to motivate this example as we will see it, and we will spend several lectures later on in the course. So consider that somehow, if I look on the picture on the left, I have three different mechanisms for generating data, and so here are my red data, my orange data, and my blue data. And later on you can think, for example, this data coming from three different Gaussian distributions, right? But so in the picture on the left, I do know what generated my red data, my orange data, and my blue data, right? So they are colored appropriately, okay? I do know what the generating mechanism for this data. All right, so now let's say that I go to the middle picture and I remove the colors and I give you these points with no color, and I'm asking you if I take any of these points, right? So if I take any of these points anywhere, and I ask you, is this point a red point, an orange point, or a blue point? Effectively, what I'm asking you is to classify for me the color of each point, if it came from the red class, the yellow class, the blue class. And that calculation is, again, a straightforward application of Bayes' rule. And again, you can see we're trying to quantify from what class C a point X came from, and the only thing that you require to do this calculation with Bayes' rule is to know the data generating mechanism for each class. That's the probability of X for each class, and of course you need to know the prior of each class, and we can assume that maybe the prior is 1/3, 1/3, 1/3. So if you do this, you can actually compute this probability. And later on, when we do classification problems, we're going to try to compute posterior probabilities that will actually affiliate each point X not only with one class, but a little bit, let's say, with the red class, a little bit with the yellow class, and a little bit with the blue class. And maybe if you can distinguish the colors on the picture in the right, these points now have a little bit of all the three colors, unless they are obviously in the blue regime, or unless they are in the red regime or in the yellow regime. In between, they have a class, they have colors that say that each point is a little bit part of the red class, a little bit part of the yellow class, and a little bit part of the blue class. And those numbers are coming by using this Bayes rule that you see on the top. Now, why, you may ask, why do we call this a generative classifier? So when we write this with the Bayes rule, it requires that you know the generating mechanism for the data for each class, and that's why we call this a generative classifier. So in some sense, what you can do is bypass completely the the Bayes rule and come up with some model for this probability without ever having to use Bayes rule, and we will do this later in this course. Obviously the advantages and disadvantages of these approaches will come later in a very clear fashion, but this setting where you compute this probability without using Bayes' rule is what is called the discriminative way for doing classification. What you see here is the generative way for classification. Now, the parameters here, theta indicated, will be the different parameters of the model. Again, this is not important what they they mean right now. So we will see this in follow-up lectures in significant detail. So for now, I just wanted to demonstrate this as a way of applying Bayes' rule to classification. All right. So we went through the slides, so there's nothing new here. So let me continue to this new concept now of independency between two events. So two events, A and B, are going to be called independent and denoted like this. So this sort of indicates like an orthogonality, at least for now. And so the definition of independence of two events A and B is when the probability of A and B is equal to the probability of A times the probability of B. And somebody who has not seen this before, it says, well, I cannot get any insights from this equation. What does it really mean? And a good way to get insights is to actually rewrite this equation using the definition of the conditional probability of A given B. And you remember this, the conditional probability is the probability of A and B divided by the probability of B. The probability of A and B for independent events, I told you, is P of A times P of B. So if you plug in here P of A, P of B cancel out, and you get this alternative definition of the independence of events A and B, and it says two events A and B are independent when the probability of A given B is equal to the probability of A. And if you think about this, makes way more sense than the original definition, because it says, you know what, the probability of A, it's independent from the fact that you know or you don't know the event B, okay, that the event B took place. So if the event took place or not has no information to offer you about A, so the condition of A given B is equal to the marginal of A. All right, so you see exactly the same definition here, and I am going to generalize this definition of independence. What you see here is what we call marginal independence, right? It involves the joint probability of X and Y and the probability of X and Y, but nothing is conditional on anything. So we can extend this and define conditional independence of the events X and Y condition on Z, where my definition is exactly the same as the marginal definition, but you notice all probabilities are conditioned on Z. When you have these conditional independence relations, don't be scared of long equations when you condition on several things, because effectively Z carries on in every term, and the independence takes care of X and Y. That's why you see X and Y here. But this equation is only true when you refer to conditional events on the event Z. And we call this conditional independence, CI relation between X and Y. All right, let me do one example to show you that things can get a little bit murky. And I'm going to take three events, and I'm going to show you that if you have three events and you try to establish if these events are independent using the definition I just introduced, pairwise independence, it will not imply that all three events together are independent. So you have to be very careful when you try to establish events of multiple independence of multiple events. So let's consider that we have four balls that we call them 1, 2, 3, 4 in some box, and we define three events. So the event x1 is that ball 1 or 2 have been drawn, x2 is ball 2 or 3 have been drawn, and x3 is ball 1 or 3 is drawn. Okay, so let's first compute if let's say events x1, x2 are independent. All right, so we're going to use our definition. So we're going to have to prove that the joint distribution of x1 and x2 is the probability of x, the product of the probability of x1 times the probability of x2. So let's see if that's true. So the probability of x1 is, it says here, x1 is when ball 1 or 2 are drawn. All right. So assuming this drawing 1, 2, or 3, or 4 are all have equal probabilities. So the probability of drawing 1 or 2 is 1/4 each of them. So the probability then of x1 is equal to 1/2. All right, everybody sees this. I have two numbers of drawing 1 or 2. Okay, there is a probability 1/4 for this and 1/4 for that. So I have a probability of 1/2 for event x1 to happen. Similarly, I have a probability 1/2 for the event x2 to happen. So the probability of the two marginals is 1/4. Now, what is the probability of event x1 and x2? What's common between x1 and x2 is that I am drawing 2. And what's the probability of drawing 2? It's 1/4. All right? So obviously this event, you know, of x1 and x2 happening together, you know, gives me a probability of 1/4, which is the probability, the product of the probabilities of the marginals of x1 and x2. So x1 and x2 are independent. Okay, that's the bottom line. And similarly, you can show x1 and x3, and x2 and x3 are independent. But let's look at the joint probability of x1 and x2 and x3. So if you look at the common elements between x1, x2, and x3, there is none of that, so that probability is 0. But if we compute the probability of x1, x2, x3, each of them is 1/2. Their product gives you 1/8. And obviously, you can see now the three events together, they are not independent. So effectively, pairwise independence, that's what this example shows, does not imply mutual independence. And also this indicates that establishing the independence of multiple events is not going to be very difficult, and it's going to be very difficult, and we're going to need sort of more intense calculations than the simple definition that we have discussed up to now. Let me do one more example with a little bit of a graphical representation. So let me take three events A, B, and C, and I'm going to put some physical meaning to those events. So A will be that the event that it will rain tomorrow. B is the event that the ground is wet today. And C is the event that is raining right now. Okay? So will you agree with me that the event that is raining right now sort of explains the event that it will rain tomorrow, or that the ground is wet today? All right? So I'm indicating that C explains A and B with these arrows here. So if I know C, that explains that it will rain tomorrow, or that the ground is wet today. So effectively, what that means is that if I know C, and that's why this event C is shown here with a dark circle. So if I know C, A becomes independent of B. In other words, if I know C, I don't really need to know anything about B to infer A, because C is sufficient to tell me everything I need to know about A. So effectively what that means is that the events A and B are conditional independent given C, and this is the definition of conditional independence. And if you want it in more compact notation, given C, A is independent of B. Knowing B does not offer any information beyond the one contained in C regarding A. Okay? So this is a very useful result of causal relations and independence, and we will see this example actually coming in other areas of machine learning, certainly in probabilistic graphical models, to come up with independence relations between random variables. In this particular example, I am going to call this event C to be the parent of A and B, and you can say here with some sort of philosophical manner that somehow knowing this root parent node makes the children to be independent, okay? Or even in more technical language, it separates the children A and B. And I know lots of these things may look insignificant in this lecture, so for now, just study this example as to the implications of knowing C, implying that A and B become conditionally independent, which is the two relations that you see with the equations on the bottom. All right. You may ask, okay, so why do we really care about conditional independence between random variables? Well, you know, if you take a case of discrete random variables, let's say we have two random variables, x and y. X can take, let's say, 5 values, and y can take 6 values, all right? So to describe the joint distribution of x and y, you need 30 values to populate this table, or even better, you need 29 because all of these values sum to 1. You remember, one of these events will happen, and all of these events happening will lead to probability 1. So this sum of all of these probabilities being equal to 1 requires only 29 values to populate this table, and the 30th value will be 1 minus these 29 values. So, to not confuse you, if we have this discrete random variables and you look at the joint, you need 29 values to describe it, all right? So you need 29 values. So if that distribution is unknown, you're going to have to compute somehow 29 values. Now, if it happens that P of x, if it happens that x and y are unconditionally independent, okay, this is what I have here, then this joint probability distribution is the product of P of x times P of y, and P of x requires only 5 numbers to describe it. I see 6 here, so 6 minus 1 gives you 5, and here I see 5, so you need 5 minus 1, you need 4 numbers. So effectively, independence takes you from 29 down to 9 numbers. And you can think if this table was a huge table with many, many values of the order of millions, using independence between events simplifies the number of elements that you have to compute, and that leads to many nice algorithms that we will see later on in machine learning that take advantage of this unconditional independence between random variables. Okay, let me introduce something that I will not really use in this course, but it's sort of so you can take this as an exercise. So let's say that we have conditional independence between x and y given z, right? So this theorem that you see here, it says that the joint distribution of x and y given z can be factorized as the product of two functions, one function of x and z and another function of y and z. Okay, and this factorization is for regions of z where the probability of z is not equal to 0. Okay, so again, if we have this conditional independence between events x and y, we can write this conditional joint distribution as the product of two functions, one of x and z and another function of y and z. So you can actually prove the following, that independence, if we have this conditional independence, it always implies this factorization, and that is rather trivial to solve, because if I do have conditional independence, then this can be written as the product of these conditional distributions, and this is my one function g of x and z, and this is my other function of this should be an h of y and z. All right, So independence implies factorization. But what is interesting is if I do have this factorization, then this factorization also implies independence. The algebra is a little bit more involved, so I'm going to go fast through it. There is no complexity, so you can actually read the slide and see the argument here. So we're going to take a factorization of this form that you see here. And so the first thing I'm going to do is I am going to integrate for all possible values of x and y. All right, for all possible values of x and y, then this sum has to be equal to 1. And if you push the summation on y to the h function and the summation over x to the g function, then we have that this summation times this summation is equal to 1. Okay, so I am going to use this, the product of these two summations being equal to 1, I'm going to use this momentarily. You can actually marginalize on y only, and if you do that, so effectively what I am doing here is, you remember we have a factorization, we have this factorization and we want to show independence. So if I marginalize this equation, so if I sum on y, on the left I'm going to get the conditional of x given z, and on the right I'm going to get a summation for all possible values of y. This is what I have. And I can do the same thing where I marginalize in x, so I'm going to get the condition of y, and then I'm going to get a summation for all values of x in here. Alright, so we're done basically with the proof, because if you multiply those two conditional probabilities and you use that these two sums, their product is equal to 1, then immediately what you can see is that the product of the conditionals is the product of g and h, and the product of g and h is basically the conditional of the joint of x and y. So conclusion, basically this theorem says that conditional independence implies a certain factorization, and this factorization on reverse implies this conditional independence. This again, it's an example of conditional independence that has a lot of implications in areas of machine learning, such as probabilistic graphical models, and if you take those courses later on, you will learn more on how this type of calculations are being used. Okay, so let me finish the lecture today with two more examples of conditional independence. Consider this as homework examples. There is nothing to memorize. And so the first example is what is called, independence relation that comes with the name decomposition. So given z, if I am saying, if x is independent of y and w, again, given z, if x is independent of y and w, implies that x is independent of y given z. So I can get rid of w in the argument here, and if this is true, then x is independent of y given z. All right, how can we prove this? Well, we can start with what we know, that x is independent of y and w given z. All right, so this implies that the condition of x, y, and w splits on the product of these conditionals that you see here. And now I am going to use this, all right, and I'm going to write the condition of x and y given z as, can you see from where this thing is coming from? All right, where did I get here? Where is this relation coming? Remember that everything is conditional on z, so there is nothing new here. But I see here a product rule of a joint distribution of x and w, and then I see a marginalization in w. So really, what I have here is the sum rule of probability. All right, so it's like I am going to write this p of x and y given z as p of x and y and w given z with summation for all possible values of w. So this is what you see here. And oops, let me go back. So I have not yet used this independence relation that comes from the left-hand side. So this is only the sum and product rules of probability. So now what I can do is I can take my left-hand side from this equation. There is no W on the first term, I can pull it outside. There is a W on the second term, all right? And this W, I can write it as, there is a marginalization here on Y, so I can write this as P of Y given Z. So immediately you can see that the conditional of X and Y is the product of the conditions of X times the condition of Y, and that leads to the conditional independence relation that I want to prove. Okay, so so effectively, let me clarify here again. I think I maybe misstated this. So here you remember the calculation on the left-hand side led us to this equation that you see on the top. Here I mentioned that I am using the sum and the product rules of probability, but actually let me revisit this to be more proper. This conditional of X and Y given Z, you can write as the sum of this for all possible values of W, and this is being substituted from what we computed from the independence relation from the left-hand side, and this is what you see here, and then the rest follows from there. So the second equation on the middle is basically a combination of the sum rule of probability, but also the conditional independence coming from the left-hand side. All right, so that's a much better justification of the proof of this decomposition independence relation. All right, let me do one more example, and that will be the end of the lecture today. So this example says that similarly as what I had before, if X is independent of Y and W given Z, then X is independent of Y given Z and W. So I can put W in the conditioning. So let me see how this can be derived. So if I use the independence, the conditional independence relation on the left-hand side, so X is independent of Y and W given Z implies that this is the product of X given Z and Y and W given Z. All right, so remember this blue line on the top. And now to establish this independence, what I'm going to do, I'm going to take the conditional of X and Y given Z and W, and I'm going to use the product rule of probability. So I'm going to bring W to the left-hand side. So this is the product rule of probability given Z. All right, I am going to substitute. I'm going to substitute the numerator with what I derive from my independence relation from the left-hand side. So this is the product of X given Z and the product of Y and W given Z. And using again the product rule of probability, I can write this ratio here as the probability of Y given W and Z. All right. So what I have is, if I can take the second line and rewrite it, I have the conditional of X and Y given Z and W is the conditional of X given Z times the condition of Y given Z and W. And here I have actually done an addition of W. I am basically saying the probability of X given Z is the same as the probability of X given Z and W. And you may ask, why is that the case? And if you remember, we just proved this in the previous slide, that if X is independent of Y and W given Z, then X is independent of W given Z. Okay, and that implies that the probability of X given Z is the same as the probability of X given Z and W. So bringing W doesn't affect X if I know Z, and that's the independence relation that we proved in the previous slide. So when you combine those two together, you can see that X and Y are independent given Z and W. All right, there is one more exercise, one more slide, and I'm going to leave you this as a homework example so you can actually try to solve this contraction independence relation that looks a little bit more complicated, but does nothing else but using the basic definitions of conditional independence relations that we saw in the earlier examples. All right, so that's our first lecture, discussing basically a little bit of fundamentals of probability, bringing the concepts of discrete random variables, and then we talked about independence of events and discrete random variables, and we will continue with more on fundamentals of probability and statistics on lecture 2 when we come back next week. Thank you.